Hi, this is Miss Litton, and this is a cacophony of children. Welcome. So you have a final coming up. At this point, if you're not here, I'm just letting you know your last set of points for the semester have been posted. So at this point, you should have your grade. And remember then, from now forward, you can choose who you're going to work with on your final for the written portion of the final. So I know there's inherent stress in that, and there's jockeying for position and potential hurt feelings. So we handle everything with sensitivity and thoughtfulness, right? So you can work with somebody that is within 10% of your grade. Right? You can work with another person that's within 10%. You need to be transparent about your grade, right? Because you don't want to invalidate your test score by not working with somebody that's within 10%. So usually it's somebody that you feel comfortable with and you've probably been working with them all along. You're probably going to continue to work with that same person, I'm assuming, if you're within 10%. If you want to choose a new person, choose a new person. Don't string someone along. Just give them an answer. Don't argue with somebody. If they say, you say, hey, do you want to work with me? And just go, it's not going to work out. Just say it real nicely, it's not going to work out. And then go, okay, and then pick somebody else. I want to firm up tomorrow so that you can move forward in your studying. So I want to firm that up tomorrow. And I'll have you at some point kind of decide, hey, I'm working with this person, and sit next to them and make a pact about it. We have some classes that have odd numbers of people. And so in those classes, I will decide who's going to be a threesome. So you can't, because usually I have one person who doesn't have someone, and I'll try to pair them up with somebody who's in the same percentage. So don't come and ask to be the 3 group. Okay, just commit to your one person. If we have some people out, we'll go, okay, let's decide who we're going to work with. Okay, so just be real clear about that. If they're good friends, you could text about it and all of that. And then let go of the stress of that, of working with somebody, and then you can move forward and be real strategic in making sure that you're reviewing. Remember, nobody can bring your grade down, right? Because you should be coming into it with a full group of information. Nobody should be taking advantage of you if you're a real strong student, because I've put the caveat in of you have to work with somebody else that's within 10%. So even if your best friend is your best friend, but there's a 20 or 12% difference, you just can't work with them. I want you to work with somebody else who's been working at a certain speed or level to you, so it's equitable, because nobody wants to feel like they're getting taken advantage of, right? So you understand that. So find somebody that you think would be about your grade level, and then work with them. If in the test you disagree with each other about something, you don't have to go with them. All you would do is draw a line, and you would say, for this answer, or on a separate answer sheet, you can say, I need a secondary answer sheet. You could add what it is. So nobody's going to make you get a score that you don't want to earn. But what you have the option of doing is discussing things with somebody else, and maybe they will come up with a better option. Okay, does anybody have any questions just about that? I'll be talking about this in class tomorrow, but you have everything in there now, so I know a lot of you are thinking about it now. Questions or concerns? Okay, so on Unit 2, I already have a full review recorded for Unit 2. I already have a full review recorded already for the essays. So let's kind of hit the big ticket items on these. On membrane structure and function, I expect you to be able to tell me the components of a membrane and the role of every part of that membrane, what role it plays, right? Okay, so if you're talking about components of a membrane, what are some components you would for sure tell me? Just start saying them. Cholesterol, and that's going to affect what? Fluidity. What's another? Oh, where wouldn't you find cholesterol, though? Plants. Okay. What else would you find? Phospholipid, and that's the barrier, right? The phospholipid is actually the barrier. And that is a phospholipid what? Bilayer. And you would explain about the phosphate groups on the edges being hydrophilic, and the fatty acids chains in the middle being hydrophobic. Exactly. Okay, what would be another component? Proteins. Okay, put a pin in that. We're going to come back to proteins, but proteins are a part of it. They serve many different functions. And what's the fourth one? Yeah, glycolipids. Yeah, glycolipids. So you talk to me about glycolipids and glycoproteins, right? Then we can talk about a lot of different things after that, right? So we could talk about, let's jump back to proteins, and you would tell me the different functions of proteins. So they could be a channel, carrier, cell recognition, receptor, enzymatic, and junction. Perfect. Then another thing I could ask you about is how do things cross a membrane? And you could say through the phospholipid bilayer, put a pin in that. There's a lot of things we could say there, right? Through the phospholipid bilayer using a channel or a carrier. It's both passively and actively, right? And then whole membrane, which is endo or exocytosis. So now we can talk about so much on each one of those. So let's talk about through the phospholipid bilayer. Who cannot go through the phospholipid bilayer? If you are what? Large or charged. Right, you're just not going to fit. Why can't you go through it if you're charged?
Because of
hydrophobic region in the center, right? Okay, so if you're large or charged, you're not going through the phospholipid bilayer. What could go through a phospholipid bilayer?
water.
Water, what else? I heard it, what? Gases, right? Now, water doesn't move through that fast because water is a what? Polar molecule. So what does it use? You're so smart. Okay, so water and gases. Now let's focus on just the water part, okay? So water passing through a membrane from a higher concentration to a lower concentration, what do we call that? What? Starts with an O. Osmosis. When you talk about osmosis and water moving, if it's moving from a higher concentration to a lower concentration, right, we have terms for that. Hypertonic, hypotonic, and isotonic. Hypertonic medium as opposed to a hypotonic. How could you describe those two? And a membrane is going to separate them. What does a hypertonic medium have?
It has more osmotically active substances.
That's exactly what I would say. It has more osmotically active substances, OASs, right, that are interacting with the water. So water must flow from the hypo into the hypertonic solution, right? And we could do a lab, perhaps, to measure that, you know, when I'm thinking about it. You know, we could have bags of various molarities of solutions, right? We could put them in distilled water, and we could take the percent change in mass of those bags over time, right? There are labs, any lab that's tied into a topic, that's a good thing. So you could talk about how the mass would change, right? And, okay, so then we talked about through the phospholipid bilayer, hyper, hypo, iso, lots of things wrapped around that. Then we talked about channels and carriers. And then we want to talk about the bigger ticket item of active and passive. Osmosis would be what? Passive. Active is anything that requires energy. Well, what happens if you just go from a higher concentration to a lower concentration, but you're using a channel? What's that called? Facilitated transport, or sometimes it says facilitated diffusion, right? And in those cases, you just have to use a channel because you're either large or charged, and that's the only way you can go, but you're going from a higher concentration to a lower. If you do the opposite of that, if you go from low to high, no matter what, that's going to be what? Active. And those are usually called what? Starts with a P. Pumps. Those are called pumps. Okay? The third way to cross was what? Endo and exocytosis. And no matter what, that's going to cost you energy, because that's a cytoskeleton moving a cell membrane, so that's going to cost you something. When I think about endocytosis, I think about 3 different types of endocytosis. Cell drinking would be penocytosis. Cell eating would be, and then
Receptor mediated
endocytosis. Okay, how do we feel about membranes? Easy peasy lemon squeezy, right?
Oh yeah.
Totally. Okay, so let's move on to metabolism, energy, and enzymes. I'm thinking laws of thermodynamics is what I'm thinking. What's the first law say? Energy is neither created or destroyed, it just
transferred and transformed.
right. And every time you lose some as
Heat.
because everything is going to greater and greater entropy, disorder, right? And to stay alive, the reason we eat food and have oxygen, besides it being mighty tasty, okay, we do that so we can generate ATP in order to fight entropy. Yes?
Yes.
Yeah.
Okay. So entropy is a measurement of disorder. Entropy is a measure. Okay. Entropy is a measure of disorder, and everything is going to greater and greater disorder. So we need to fight that. Okay, we just did laws of thermodynamics. We did entropy. Then did we go right into enzymes? Oh, we probably talked about ATP, adenosine triphosphate, adenine, ribose, phosphate, phosphate, phosphate. Ooh, we probably talked about ender and exergonic reactions, I'm guessing. What do endergonic reactions require? Input of energy, right? Right? If we measure the free energy, our products have what? More or less?
More. Less.
On which one are we talking about? In endergonic reaction, they would have more. In an exergonic reaction, they would have less. Okay? Exergonic reactions are often called spontaneous because we know we're going to greater and greater entropy, so objects want to break down, right? What do you call that hurdle that prevents spontaneous reactions from occurring? Energy of activation. Exactly. What is something in general that could lower the energy of activation? Starts with a C. Catalyst. A organic protein-based catalyst is called enzymes. Yeah. So enzymes lower the energy of activation to make reactions more likely to occur. What prevents endergonic reactions from just spontaneously occurring? You need to put energy into them. So unless the energy is provided, then it's not going to happen, right? We're more worried about the exergonic reactions, right? Okay, so enzymes increase the rate of reactions by lowering the energy of activation. Okay, so what's the special part on the enzyme where the substrate binds? Active site. Anything that influences the shape of the active site will influence the activity of that enzyme, right? So let's think of some things that could influence the activity. See how it's just a story? It's just a story. You know the story. What's something that could influence the activation site? And that's one of them. Yes. What could influence it?
Temperature.
Temperature will make any reaction go faster. You're absolutely right. But how could temperature affect the active site? It could denature it. Yeah. Generally speaking, if you increase the temperature of any reaction, the reaction will go better up to the point that you what? Denature the enzyme. Exactly. Because you have more kinetic energy. What's something else that can affect it? Start saying it. pH. Yes. What? Concentration. An inhibitor. Exactly. Okay. Now, what kind of inhibitor actually binds to the active site? Competitive inhibitor. So it's competing with the enzyme, competing with the substrate for the active site on the enzyme, right? A non-competitive, which of course you know, a non-competitive inhibitor does what? It binds to a secondary site, which we call the allosteric site, which then changes the active site. Sometimes that can be really good because it can give feedback. We have enough product, that product acts to bind to an allosteric site, which shuts down that enzyme so it doesn't work any longer. Do we hit everything on that? I'm just trying to remember off the top of my head. Yeah? All right. Metabolism, energy, enzymes. Okay, we're ready to move on. Let's talk about photosynthesis. All right? Let's do our song. We should really do both songs all together, don't you imagine? Yeah. But let's talk over them first. Yeah. Okay. So for photosynthesis, let's think big ticket items here. Photosynthesis is Photosynthesis is dependent these are organisms that can take inorganic molecules and make what? Organic molecules. The inorganic to the organic. Okay, what is that going to require? What? ATP. Exactly. What else? A source of carbon. Is that what you're going to tell me? Yeah. And a source of electrons, perhaps? Of course. Yeah, water is your source of electrons. To get ATP, you're going to take energy from the sun and use an electron transport chain to make a chemiosmotic gradient in order to synthesize the ATP, right? Okay, and your source of carbon is carbon dioxide, which comes through the stomata, which you hope is open, because if it closes, then you know what RUBP does, right? What's that called? Photo respiration, right? When she acts like a gardening tool that's not a shovel, right? Okay. Yeah, not a rake. Oh, sorry. Once you have sugar, you're taking inorganic gases, CO2, energy from the sun, a source of electrons, and you're building sugar. Then all cells can do the next process, which is called cellular respiration, where you break down those sugars in order to generate more ATP. So you can use that energy that's generated in your mitochondria to be a source of energy for any of your anabolic reactions or the beginnings of catabolic reactions in order to fight entropy, right? That's the whole purpose behind that. So if you're going to do photosynthesis most efficiently, are you going to do cyclic or non-cyclic?
Non-cyclic. No, cyclic.
Non-cyclic. Okay? Because you want, I know, the one time, right? Okay, so non-cyclic, you have electrons come in and electrons go out, and you have the ability to make ATP and reduce NADP, which you can take both of those to the right. If you're going to do cellular respiration, what's the most efficient one? Aerobic respiration. Right? Oxidative phosphorylation. That's a question right there. Is what are all the different kinds of phosphorylations we've learned about? Substrate level, oxidative, photophosphorylation. Remember that? Absolutely. Okay. So let's start with cellular respiration. Here we go. What's the whole thing called? Life. Okay. The whole thing's called life. Okay. We're going to do cellular respiration. What's the first step called? That is so weak. Get it together. What is it called? Glycolysis. Who does it? All cells. Where do they do it? In the cytoplasm. What do you start out with? Glucose. How many carbons? 6. What are we going to do? Break it in half. How many steps? 10. How many enzymes? 10. What are these called? 2 pyruvic acids. And you reduce some NAD and make some ATP. 2. Well, we have plenty of oxygen. What should we do? Aerobic respiration. What's the next step called? Transition prep. Here we go. We're pulling off a carbon and CO2, yeah? And you reduce some NAD and 2 acetyl-CoA, put 1 away. What's the next step called? Citric acid cycle. What's another name for it? Krebs cycle. How many times are we going to do it?
Twice.
Why? 2 acetyl-CoA. What does it mean to do the bit? Reduce an NAD and pull off a carbon dioxide. You ready? 2 plus 4 is 6. Do the bit, get 5. Do the bit, get 4. Make an ATP. Reduce an FAD. Reduce an NAD, and 2 plus 4 is 6. Do the bit, get 5. Do the bit, get 4. Make an ATP, reduce an FAD, reduce an NAD, and stop. Gather all your reduced NADs and FADs and take them to the top of the ETC. Pause. Where are we exactly?
The ETC.
The cristae of the mitochondria. That inner membrane, right? The folds. Okay. Why do we go, Yeah, NAD comes in at the top, FAD comes partway through. Okay. Gather all your reduced NADs and FADs and take them to the top of the ETC. Reductase. What are we doing? Taking hydrogens, taking it from the matrix and putting it out into the intermembrane space. Got it? Reductase, cytochrome oxidase, and you make some ATP. A lot of it, a lot of it, a lot of it, or a lot of it, a lot of it. Who catch electrons at the bottom? Oxygen forming water. Water, 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 water. What are we going to do? Break it in half. What do we get? Oxygen and electrons. Sweep, sweep. What are we sweeping? From who? Water. Sweep, sweep. What system are we in? Photosynthesis 2. Here comes the sun, traveling in waves. Particles of light are called photons. And it gets the electrons excited. PQ. Where are we?
Photosystem 1.
Thylakoid membrane. Bringing hydrogen ions from the stroma into the lumen of the grana, right? Okay. PQ. And you make some ATP. Photosystem
1.
Here comes the sun, traveling in waves. Particles of light are called photons. And it gets the electrons excited. Who catches it? NADP, forming reduced NADP. Then you take some ATP and some reduced NADP to the dark reaction, or the Calvin cycle, or the light-independent reaction. Ready? 3C5. Stop. What's its name? Say my name, say my name. RUBP. Okay, now who is RUBP supposed to hook up with? Carbon dioxide. Good. But if CO2 levels are low because the stomata are closed, because it's hot, then who might it hook up with? What are some adaptations in order to avoid that process, which is called photorespiration? What can we do to avoid that? Can plants who fix CO2 at night, right?
C4 plants.
PEP, and yeah, you're just going to let me finish sentence, and then C4 plants, right? What do? PEP escorts the CO2. Remember the bundle sheath cells around the xylem and the phloem? Okay, here we go. 3C5 plus 3C1 makes 3C6. Break down to 6C3. Use some ATP, use some reduced NADP. Pause. Where did we get those?
From the light-dependent reaction.
Light-dependent reaction, okay. Use some ATP, use some reduced NADP on your 6C3. Take one away, PJL, G3P. And you're left with 5C3. Use some ATP to build 3C5 plus 3C1 makes 3C6. Break down to 6C3. Use some ATP, use some reduced NADP on your 6C3. Take one away, glucose. Wait, do you really have to make glucose? No, you could leave it as G3P, PJL, because it's the building block for amino acids, right? You can make fructose, you can make starch, you can make oil, yeah? Okay. Take one away, glucose. And you're left with 5C3. Use some ATP to build 3C5. Stop. Pick up your glucose. How many carbons?
6.
What are you going to do?
Break it down.
Steps.
10.
Enzymes. 10. What are these called?
2 pyruvic acids.
And you reduce some NAD and make some ATP. 2. Oh no, we don't have any oxygen. What are we going to do? Fermentation. How many choices do we have? 2. Do we get to do both of them?
No.
No, it depends on what organism we are, right? Okay. Oh no, we don't have any oxygen. What are we going to do? Fermentation. How many choices do we have?
2.
You and I make lactic acid. Makes our muscles sore. Plants and yeast make alcohol. Does it make it permanently when we make lactic acid? Is it there forever?
No.
You can reverse it when you have some
Oxygen.
Okay. Alcohol. Either way, you oxidize your NAD. Yay. Okay. Yes.
Plants also make.
Stop. I want to hear a question. Shh. Go.
Plants also make CO2 when they make alcohol, right? Or,
Yeah, that's why we them.
Oh, okay.
Yes. What else? Yes.
The acetyl-CoA groups, what was the point of having acetyl-CoA?
Acetyl-CoA is what you need to enter into the Krebs cycle.
Okay, it's just like a cake.
Yeah,
Okay.
it's acetyl-CoA. There's a coenzyme that escorts it, that allows it to bind to the 4 carbon that's already in there.
Got it. Thank you.
Okay, what else? Did you do a lab on photosynthesis?
Yes.
The leaf disc?
Yeah.
And you floated based on the amount of carbon dioxide or light you had? Yes. Okay, what else? Did we do an enzyme lab?
Yes, we did.
What was our enzyme lab?
Catalase.
Catalase, breaking down what? Hydrogen peroxide into what?
Oxygen.
And water. What did we measure?
Oxygen.
Oxygen production, right? And I think in our lab we vary the concentration of the substrate. But we could have varied the concentration of the enzyme, or we could have varied the temperature. Any of those things would work. What else? Okay, check. Unit 2. Identify yourself. When we were talking just now in the last, we've been talking for 26 minutes, covering 4 chapters and 3 labs in 26 minutes. Excellent job. Where are your weak spots? Where, when we were talking and other people were spitting out answers, you were going, oh, damn. Okay. Were there any spots like that? Those are the parts. Listen to me. Don't keep reviewing the stuff you know. Find your weakness. Find your weakness and go review that, right? Strategically. Study something tonight, yeah? Okay, I love you. Any other questions? Oh, wait, another question? Yes.
Well, just knowing, because my class in general had trouble with this one, for the lab with pH, if you're varying pH, would you vary the...
You never vary pH.
Okay, so how would that
If you
lab
vary the
be
pH,
made?
then your enzyme shouldn't work. Because remember, every change in pH is a 10-fold different in concentration of hydrogen ions. Temperature you can vary. Usually the higher the temperature, the faster, because they have more kinetic energy. The molecules will move faster. You get more product up to the point where you denature. Yeah.
So if you're going to propose a lab with pH, how would you vary that to see how the enzyme, how it's a...
My prediction would be that if it required an enzyme with that functions at a pH of 3, then I would bet at a pH of 5 it wouldn't work as well and I wouldn't get as much product, or a pH of 1 it wouldn't get as much product.
Okay.
That's what I would predict.
Thank you.
Yes.
So for that pH lab, would your control be the optimal pH of
Yep.
the enzyme, or
That's what I would do.
pH 7?
Yeah, I would probably do whatever one of that particular enzyme, but you could put 7 if you wanted to, and then see how it is. It would be hard to predict after that.
Okay. But optimal pH would work.
Yeah.
That's what
What else? More questions? Yes.
For the varying amounts of ATP produced in cellular respiration,
Yeah.
do we have to like worry about like the specific numbers, because it
Well,
varies
remember when
from-
we talked about in an ideal world, right? If we didn't have the second law of thermodynamics, you would make 3 ATP for every strong NAD and 2 ATP for every weak. But we live in a world with the second law of thermodynamics is applied, so you only get about 2.5, and I would know that. Only 2.5 ATP for every strong NAD and only 1.5 for every weak, for every FAD. And remember, the 2 NAD from glycolysis sometimes go in strong, sometimes go in weak, and that's because they're out in the cytoplasm and the electron transport chain is occurring in the mitochondria. So sometimes it just transfers that energy to an FAD to have it take it in there instead of itself. Remember, the reason why you do fermentation is you have to generate NAD-OX back if you want to do glycolysis again. That's when we have a problem, is if we don't have a source of NADs that are oxidized. Question? Did I see hands somewhere? I saw a hand. Yes.
Hello.
Hello.
For the NAD that you said could be weak or strong, that's why there's a variation of 36 and 38.
Mm-hmm. In the ideal world.
Okay.
Yes.
When we get to see the test, the one we just did like yesterday.
I think probably our next review session, whenever that is.
Oh.
You're welcome.
So on Friday.
I don't know when it is.
Friday.
Friday? Yeah, we'll do Friday.
We can see you on Friday.
Yeah. Or guys, tomorrow in class more than likely because we're gonna be done early. We don't have that much left to do.
Awesome.
Yeah, so we should be able to handle it in class. Remind me. Talk to your partners, okay? Talk to who you want to work with. Don't string anyone along, okay? Just be honest. Just say it's not going to work out. And just accept that and move on. Don't waste energy fretting about it, okay? Move on. Don't waste any ATP. You're super smart. Have a piece of toast.